screen, could it be?
Okay, just a moment. Srijit, can you check?
Yes, sure, yeah.
Okay, I think now I should be able to share my screen. Okay, I hope you can see my slides.
Yeah.
Okay, perfect. Yes. Okay, thank you very much. In case I'm a little bit late with my talk, please feel free to interrupt me. I can also finish sooner. So yes, I wanted to talk about using balance laws to test gravitational waveforms. If you are interested in this subject, you can have a look at this pedagogical introduction into this subject. There I give really very easygoing introduction about all these concepts and how we can use balance laws to test gravitational waveforms and directly actually also the gravity theory itself. Okay, so let me then start. As you know, when we talk about gravitational waves, the main progenitor is like the main objects are the black holes, and so what are black holes? We all know a black hole is a region of space-time where gravity is so strong that not even light can escape, and this is a direct prediction of general relativity actually. And so more mathematically, the Schwarzschild black hole is a vacuum solution of Einstein's field equations, which satisfy certain criteria that is applied to isolated system with the cosmological constant being 0 and spherical symmetric space-time and static space-time. So satisfying this condition, you can then get the Schwarzschild black hole solution. And so what you have to impose is basically that your metric satisfies certain conditions, that the Lie derivative associated to time translations and rotations vanish. And so the first condition is the stationarity, that it means that you have a time translation invariance in your background metric. And the other ones, as I mentioned, these are rotational symmetry. And so when you impose these conditions on your metric, then your metric has to have this very specific field configuration. As you can see, only certain components survive and they have only R dependence. And then you can insert this ansatz to the Einstein's field equations. And in order to solve these equations, you have to introduce further conditions actually, namely very specific boundary conditions. And one specific condition is namely that the spacetime is asymptotically Minkowski, meaning that if you go at far infinity, your metric should mimic Minkowski. And the second condition that you have to impose is at this far infinity from the source, we should recover Newton's law. And this fixes the coefficients of your Schwarzschild solution in this very specific form. And these boundary conditions do not completely fix the solution, actually. We still have gauge freedom. And different gauge choices might give rise to different looking solutions. For instance, the Schwarzschild gauge, in that case, the metric ansatz looks in this very specific way. You could also choose a different gauge, like this one, for example, where naively you see that there is this off-diagonal term, but nevertheless your static spherical symmetric solution is imposed. Okay, so even though these solutions look different, they are physically exactly equivalent and they agree on all physical predictions like gravitational redshift, time dilation, bending of light, existence of event horizon. But you have to go through these steps. Imagine you change your gravity theory. It's not general relativity anymore, but something else. You have to go through these steps that I just introduced here. Okay, and one important theorem is the Birkhoff theorem. which states that any spherically symmetric solution of Einstein's vacuum field equations is necessarily, in order to have Schwarzschild solution, in particular, it is static. And the important consequences of that is that spherically symmetric pulsating stars do not emit gravitational waves. So this fact follows also from the quadruple formula. So if you want to have black hole solutions, as I was telling you, you have to satisfy certain conditions, assumptions, and then depending on the properties of the considered matter or object, you can have different type of solutions. For example, you can have Schwarzschild solution, where you have only the mass of the black hole. You can have a Reissner-Nordstrom solution. If this black hole is also charged, then you have the associated charge. Then you can have, rotating solution. If this has also angular momentum, this is the Kerr solution. And it can also have all of them at the same time. So it can be charged and rotating. Then you have Kerr-Newman solution. And so one very important theorem within this different black hole solutions is the no-hair theorem, which basically states that all stationary black hole solutions of the Einstein field equations coupled to the standard model matter field are completely characterized by only three measurable parameters, which is given by mass, charge, and the angular momentum. So when two black holes merge, the system is highly non-spherical and non-stationary, and therefore the no-hair theorem is broken. And because of that, you have the hope to then emit gravitational waves. So if you have just a single black hole, boring, sitting there, you will not have gravitational wave. And therefore, you really need to have a merging of two stars in order to break the spherical symmetry and to break the stationarity. Okay, so here is the two black holes, right, merging together. And as you can see, it's highly non-spherical and highly dynamical. And due to those two effects, we are able to emit gravitational waves, and we have the hope to actually measure these gravitational waves. Okay. So then let me introduce gravitational waves in a nutshell. So gravitational waves are ripples of space-time, and they give rise to changes in lengths and shapes. Nevertheless, it's not so easy to measure these changes because they're really super duper tiny. As you can see, 10 to minus 18 meters. Nevertheless, we are now able to measure them. And now there are important questions when we observe gravitational waves, like how do we extract information about the masses of the binary system? And how do we know the distance and the location in the sky of the binary system? How do we determine the total power emitted? And how can we test different theories of gravity, if it's GR or something else? And the answer to all this question is gravitational waveforms. Maybe at this point, could you remind me how much time I have? So that I just know.
Yes, just one moment, please. I think close to 20 minutes.
The total amount is 20 minutes?
I will just clarify that.
No, I mean, you have at least 40 minutes.
Yes,
okay.
40 minutes, huh?
Okay, good. Because, I'm giving a little bit long introduction. I wasn't sure if I should hurry and make it quicker. Okay, so in order to answer these fundamental questions, the big answer basically to all of this question is gravitational waveforms. So, as you can see here in this visualization, you see there are like different black holes, different objects involved. And depending on their masses, you see these wiggles, they look very different, right? And so by observing these wiggles, which is the gravitational waveform, you can try to extract all the information about the masses, their distances, their inclination, so the parameters involved, the theory of gravity. Yeah, so everything, all the physical information is encoded in these wiggles. And our task as physicists is basically to understand these wiggles and to theoretically predict these wiggles and then compare these wiggles to the observed wiggles and see how the parameters match together. Okay, so far so good. Here's one very particular example where you can see the strain of the gravitational wave plotted with respect to time. And this is this typical waveform, these wiggles that you can see. And as I was mentioning, all the information is encoded in this wiggle. And for example, from the frequency evolution, you can infer the involved masses. From the amplitude and the inferred masses, you can infer the distance. And from the time of arrival, the amplitude and the phase at the detector, you can infer the sky location, and so on. This is just to give you an example. Okay? And in standard general relativity, you have these two strains, these two polarizations that you can measure. Basically, they are called H plus and H cross. And they can be visualized by the way how they change test masses. So when there is a wave with this type of polarization, how does this test masses change? And here you can see for these two different polarization and waves, you see that the H plus does this movement and the H cross does this movement. And you can extract all the necessary physical information from these two polarizations. If you had another different metric theory, another different metric gravity theory, of course, on top of the standard tensor polarizations, you might also have additional scalar polarizations or additional vector polarizations. Okay, in general relativity, as I was saying, there are only these two tensor polarizations. Okay, in order to get this waveform, theoretically, right, you have to now come up with a prediction, with a theoretical prediction. And in order to have your waveform, you have to solve Einstein's field equations. But they are not so easy to solve, and it's very highly non-trivial. And because of that, what one typically does is one looks at the different parts of this merger event and uses different theoretical approaches to calculate the waveform. For example, at the initial phase, when the two objects are sufficiently far away from each other in this inspiring phase, one uses the post-Newtonian approximation. It's basically perturbation theory in order to get your waveform. But at some point, these two objects come too close, which is basically the merger phase. And there you cannot use analytical methods anymore. You really need to do pure numerical relativity approach in order to get this wiggles, this waveform. And then once the objects merge and you have your final object, which is the ring down phase, you can then apply again the perturbation theory, and it's much easier to do the calculation. But as you can see, you have these three different phases. And in order to get the full waveform, you have to now glue together these three different phases and match them in a correct way. And this is really very, very difficult. And you will introduce a lot of mistakes and errors if you are not careful enough. Okay. As I was mentioning, these three phases of waveform require very different approximation techniques. So post-Newtonian approximation for the inspiring phase, numerical relativity for the high highly nonlinear merger phase, and then perturbation theory again for the ring-down phase. To get the full waveform, it is necessary to combine these approximated phases together into a so-called waveform model. Okay, this is basically what you have to do. And there are many different waveform models, okay, in the literature. And I'm giving here some list. This is please not exhaustive. So if I don't mention your favorite waveform model, please excuse me. I'm just trying to give you examples. For example, there are these SXX waveform models. Then there are these pure and hybridized NR surrogate models, effective one-body models, and some phenomenological models, and many, many more models derived from them. And they all use different techniques and approximations in order to get the waveform. So as I was saying, discussing these models in detail or to discuss all of the existing models is outside of the scope of this talk. So what is important to us is what these models have in common and what distinguishes them. So because as I was telling, waveform models are really the essential tools in order to be able to detect gravitational waves, and also for parameter estimation, we really need to investigate them in very much detail. And as I was telling you, each model uses different approximation and different theoretical approaches, and therefore they will introduce different parameters as well. And each model typically depends on 10 intrinsic parameters and 4 extrinsic parameters. For example, as intrinsic parameters are the true masses of the involved objects, the individual spins, the eccentricity of the orbit, the orientation of the orbit, and so on. And extrinsic parameters are like the luminosity distance from the source, or the parameters determining the orientation, and so on. So you have your waveform model, which uses a very specific approximation and specific parameters. And you can then take this model and compare to observation, and first of all, use that as a detection of gravitational waves, and also use that as parameter estimation. And yeah, and each model makes simplifying assumptions, so they are not 100% exact concerning the physics involved. So examples, effective one-body models assumes a small mass ratio of the binary, and many of the older, at least older models, they, for example, neglected completely the gravitational wave memory effect, and so on. So sometimes these models can really even lack very important physics involved in this mergers. And another very important point is that each model needs input from numerical relativity for the merger phase, but numerical relativity simulations are really very expensive. Therefore, one can only cover finitely many points in parameter space, and also each model needs to interpolate between these NR data points. So you have only a few points in the parameter space, and then you have to make interpolation between these points. And each approximation technique introduces errors, and these errors can then propagate through your waveform. And so you have to understand how much error you are doing. And so given that waveform models play such a crucial role in first detecting the gravitational wave events and in extracting information from the signal, we have to ask some very crucial questions. So, for example, which of the many models can we trust when we're analyzing observational data? And which models is the closest to what full nonlinear GR would really predict for the physics of the compact binary coalescence? So if you had the perfect universe where we had the infinite amount of computational tools, what is the closest to this full nonlinear GR prediction? And can we test which model makes the smallest error and provides the best approximation? And the answer to all this question is yes, we can use the so-called balance laws. And so let me then introduce what these balance laws are. Understanding how gravitational waves are described in the full nonlinear theory opens the possibility to develop exact mathematical tests for waveform models. These are these balance laws. So these are really mathematical tests that you can apply to your model. This is, for instance, a recent idea based on this paper here. If you want to have a look on this pioneering work, please have a look at this very nice paper. So the idea, let me give you the idea behind the balance law, is very simple. So binary systems lose energy because they emit gravitational waves. And the total energy loss has to be balanced by the total energy carried away by the gravitational waves, right? This makes total sense. And this balancing of energies allows us to test and compare different models. So as I was telling you, in order to maybe have a more pedagogical introduction, you can have a look at this paper here. I would like to use this opportunity to introduce first mechanical balance laws, just to really rigorously explain to you the concept behind balance laws, and then we will exactly use the same analogy to more complicated nonlinear general relativity. Okay, so let's illustrate this idea in more detail using a mechanical analog. And imagine you have a dissipative mechanical system. Doesn't matter, it could be a relativistic or non-relativistic system, maybe two balls, right, interacting in a specific way in this mechanical system. And now imagine you put a specific boundary around this system, which is here given by this red line. And then there will be some energy influx into this system and some energy outflux out of this system. And the energy, of course, is not conserved in this system. The system is losing energy. But nevertheless, the total in-out flux of energy has to balance the total gain and loss of energy in the system. Okay, so the energy that enters into the system has to be balanced by the energy or gained or lost that goes out of the system. So imagine we measure the energy of the system at some initial time and some final time. And therefore, the measurement will yield some specific energy at this initial time and some specific energy at the final time. And now we can prove mathematically exactly that the difference between the final energy and the initial energy is given on the right-hand side by this expression, which is basically the time derivative of your Lagrangian associated to this system, and then you perform this integral. Okay, so on the left-hand side, you have the total energy gain and loss of the system. And on the right-hand side, you have the total energy in and out flux through your boundary of the system. And this total energy in-out flux is measured by the integral over time derivative of the Lagrangian. Okay, so this mathematical law allows us to test approximate solutions to complicated equations of motion. So the strategy is as follows. Derive equations of motion from your Lagrangian, make simplifying assumptions or approximate equations and solve them either numerically or analytically, depending on whether or not it's too difficult. And then plug this approximate solution into this unapproximated, unsimplified balance laws. And then you will see the amount of error you made by your approximative solution. And the better the balance laws are satisfied, the better the approximate solution describes your full, correct physical situation. Let's give me an example. Imagine you have a rolling ball with friction. So consider a ball here sitting, and it rolls down this half pipe with friction. And for simplicity, we will assume that this ball is just a point particle and there is no air resistance. And so the equations of motion are still nevertheless nonlinear and given by these equations. As you can see, because of this term here, the equations are highly nonlinear, which makes them a little bit harder to solve. And this term here is the friction term, and this term here is the nonlinear term, which makes it difficult to solve. Therefore, we can make, for example, a small angle approximation, and then this becomes linear. And then we can see with this approximate small angle approximation, can we find simple solutions? Of course, we can find them. So this is, for example, one analytical simple solution here for this angle, which is given completely analytically based on this linear approximation. And then we can now take this and then see, actually, it describes more or less nicely the physics going on, how this ball drops down here. Now, of course, the question is, how good is this approximation? How well does it describe the previous full equation, which was highly nonlinear, right? So we plug this approximate solution into the unapproximated balance laws and plot the situation. So here is an example. Here is the energy difference with respect to the angle involved, this angle parameter. In red is the left-hand side of the balance laws, basically the energy difference. And on the blue line is the right-hand side of the balance laws, which is basically the in and out energy flux through your boundary. And the yellow one is the ratio between them. So if your solution is physically 100% correct, then this ratio between the left-hand side and right-hand side should be 1. And as you can see here, only for small angles, this approximate solution is good and your balance law is satisfied. But as soon as you go to larger angles, this approximate solution is not correct anymore and your balance laws are not satisfied. Okay, so approximation good only for small angles, which we were expecting anyways, but this balance laws really gives you a way of seeing how much error you did. Okay, so for each parameter value, you can then test how this balance law is satisfied. And for certain values involved in your approximate solution, the balance law will be satisfied in a certain way. Okay, so here, for example, for a different change value of the parameter, approximation is still good, but worse at this point in parameter space. Okay, now I would like to go from the mechanical to the more complicated general relativity balance laws. As I said, you can have a more detailed exposure here from this article. I will try to use the remaining time to explain the idea now behind the balance laws in general relativity and how we can use them in order to test waveform models. Okay, so we can apply the same ideas to general relativity to compare and improve waveform models, determine which model performs better in which region of parameter space. And in order to do that, so let's remind ourselves that balance laws are really exact mathematical relations of a theory without no approximations, right? And to develop balance laws for coalescing binary system, we need to understand gravitational waves in the full nonlinear theory. which is a highly complicated subject on its own. A detailed introduction you can find here in this notes here that I am showing. And as I said, I will not be able to give you all the details here. It's quite cumbersome and very lengthy, but nevertheless, I will just try to introduce you the important concepts. Okay, so we consider a binary system of compact astrophysical objects, two black holes, and we choose our coordinate system such that in the distant path, the observer is at rest relative to the center of mass of the system. And due to the emission of gravitational waves, now there's an outflux of energy. And we can then, we can then use this signal in order to, so we can then mimic that the signal is measured at far infinity, which I am depicting here with these detectors. And the signal allows us to determine certain physical quantities, for example, the kick velocity. So when the two objects merge, the final object can get a kick. This is given by this kick velocity here. And then the total mass of the binary system is a measurable object from the signal. And then the mass of the remnant, so the mass of the final object, can be measured by the signal. So these are the gravitational balance laws. I am just showing them to you, that they have this form. As I was telling you, deriving them is rather cumbersome and a bit complicated and lengthy, but they have to have this very specific form. You have the left-hand side given by the mass and the kick velocity, and then you have the right-hand side. So observe the very close resemblance with the mechanical balance laws and with the gravitational balance laws. On the left-hand side, you always have the energy difference between initial and final state of the system. Here, as you can see, is c squared m is the energy of your system between the final and the initial state. And on the right-hand side, you have the total energy lost by the system. So the energy that is carried away by the gravitational waves. So this represents like this derivative of the Lagrangian in the mechanical balance law that we saw. So this is analogous to that. But you can see there is this additional term that we didn't have in the mechanical balance law. And this is a completely new phenomenon, which is relevant and present in general relativity, and is the gravitational wave memory. And it has this very specific form. And so if you have a waveform model that doesn't correctly have this phenomenon of gravitational wave memory, then it will not satisfy correctly your balance laws. Okay, so observe that this memory term is essentially the difference of the two values, h plus and h cross, at distant future and at distant past. And in the distant past, before any gravitational wave has been emitted, you would naively expect, oh, there was no gravitational wave, so the strain should be zero. And also in the distant future, after the gravitational wave has long passed, one should expect that the strain should be zero. And therefore, when you build the difference, you would naively expect that this should be zero. However, general relativity explicitly predicts that the polarization in the distance past and in the distance future can differ from each other and give rise to something non-zero for this memory effect. Okay, so this difference has a very clear interpretation in terms of a ring of test masses And imagine a gravitational wave passes through a ring of test masses, and as we have seen, they start oscillating. And of course, the proper distance between these test masses is a function of the strain of the gravitational waves. And after the wave has passed, one would expect that the strain is zero, and therefore that the original ring configuration would go back to its original configuration. However, GR, as I said, predicts that in general, the H plus H cross after the passage of the wave is actually non-zero. So this means that the proper distance between the test masses is permanently changed, and this means that the shape is permanently shaped, and this would mean that gravitational wave memory effect is a prediction of general relativity that gravitational waves gives rise to a permanent displacement of test masses. Here you can see when such a wave passes through a ring of test masses, once the gravitational wave passes, there is a permanent deformation. Okay, so the ring configuration is very different after the wave has passed. And in the waveform model, you see that there is this shift in the amplitude here, which is raised. And so instead of going to the initial starting point where it started, it has this permanent deformation. Okay, so I am here showing you like a very simple waveform model. This is a completely analytical gravitational waveform model, actually for undergraduates, which is very nice. So you can take this and play with this waveform model. So we assume that there are these two objects with masses m1 and m2, some zero initial spin. They orbit with each other with a time-dependent separation r of t, and they have time-dependent orbital frequency, and you can analytically find concrete analytical solutions for the inspiring phase of the waveform. And for the numerical relativity, you can make a numerical fit to numerical simulations in terms of amplitude and phase, what has been done in this paper. And so then the inspiring and the merger ring down waveforms are then matched into a single analytical waveform. Here I am plotting the waveform model that you get if you follow this example in the paper. And now the idea would be we would take this concrete solution. So we take this waveform here, which is given analytically, and then we plug this into our balance law and then check how good it does the job. So on the left-hand side, since in this model there was no kick velocity, it's given just in terms of this formula with kick velocity being 0. And on the right-hand side, they also didn't have any memory in this waveform model. So it's just simply given by this basically simplified version of the balance laws. And then we can then plug in our very specific strain, analytical strain. And here I am plotting the radiated power in order to compute basically the right-hand side. And as you can see here, you get a specific value for this right-hand side. And then for the left-hand side, I have taken as an example the first ever measured gravitational wave. And it gives you a very concrete number. And now you can compare this concrete number from the left-hand side with this concrete number for the right-hand side. And if there is a mismatch, you have then a way of knowing by how much error your approximated model is making. Okay, summary. So using balance laws, we can compare and improve waveform models, determine which model performs better in which region of parameter space, and that finishes my summary. I'm very sorry if it took longer than I was supposed to. So I'm happy to take any questions.